Saturn, wrapped in swift-moving bands of powerful storms, encircled by ever-evolving rings of rock and ice. Right now, the most advanced interplanetary spacecraft ever launched by NASA sweeps through the Saturnian system on a 4-year mission to orbit the planet and release a probe to investigate Saturn's moon, Titan, the only moon in the solar system with its own atmosphere. A mysterious, shrouded world that just might resemble a primordial Earth. Cassini-Huygens has already photographed some of the moons and made groundbreaking discoveries about Saturn. We'll go inside the restricted facility where the spacecraft was built, find out how it ingeniously navigated the solar system and communicated with Earth on its 7-year journey, and learn what dangers and obstacles it overcame to bring us to the doorstep of this strange and powerful gaseous giant. A rendezvous with the ringed planet. June 30th, 2004. Hitting speeds of nearly 60,000 miles per hour. Fast enough to get from New York to Los Angeles in under 3 minutes, the Cassini-Huygens spacecraft slipped between 2 rings of Saturn and fired its rocket for the longest orbit insertion burn in history. That engine burn had to work. There were no second chances. Because if Cassini did not slow down enough to enter Saturn's orbit, the spacecraft would have simply flown past Saturn, lost to the far reaches of the solar system, forever.
It was a very tense, nail-biting moment at JPL. Our spacecraft had to dutifully execute its commands to light up the main rocket engine for 96 minutes in order to slow down and become a natural satellite of Saturn.
43 will continue to configure for the high-gain comm, but 14 is actually configuring to see if they can lock on the carrier.
Yeah, what are your tick marks?
Although this room is called Mission Control, the scientists and engineers at these monitors were at that moment not in control of Cassini.
One-way Doppler from DSS-14?
That's affirmative.
Their first instructions to send Cassini into orbit had long ago been relayed to the spacecraft, and Cassini was, hopefully, obeying those instructions.
Saturn is a long ways away. Right now it's about 9 AU, which means it's 9 times further from us than the Earth is from the Sun. So it takes about 1 hour and 20 minutes for a signal to get from the Earth to the spacecraft, and then another 1 hour and 20 minutes to come back. So if we want the spacecraft to do something, we have to wait almost 3 hours from the time we sent the command till the time we find out if the spacecraft accomplished what we asked for.
And so, if the Cassini rocket misfired or failed to shut down properly, the team here at JPL would not have known until 1.5 hours after the failure. Far too late to save the spacecraft from disaster.
In order to go into orbit around Saturn, Cassini flew between a gap between the F ring and the G ring, and that gap is about 30,000 kilometers wide. That sounds wide, but in comparison to Saturn plus its ring system, that's actually a very small area to target.
Cassini ceased firing one engine. The other one is solely for backup. The propulsion system was then covered.
There's a protective cocoon over our 2 rocket engines as well, called the main engine cover. It looks something like a baby carriage, and we use this to protect the main engine coatings from particles, particularly in the Saturnian system.
The 96-minute engine burn reduced the speed of the craft by 1,300 miles per hour. And after a 7-year flight, the International Cassini-Huygens spacecraft was in orbit.
We've got it. We gladly now turn this from an engineering mission over to our scientists. Have fun in the Cassini playground.
Then we turned the cameras and looked down at the rings, and we saw incredible, exquisite detail in the rings. In some cases, resolution as fine as 100 meters. And this is the best view we'll get of the rings throughout the entire mission. So I'm glad we had a chance to do it.
So why spend decades of development and $3 billion to research and photograph a world so far and so different from our own?
Saturn is one of the most interesting destinations in the outer solar system. It has these very, very large and obvious rings. So obvious, so large and so spectacular.
In a sense, it's a miniature solar system. You have the planet Saturn, 31 moons around it, and we think that the formation of Saturn plus its rings was very similar to how the solar system as a whole formed.
And the Saturnian system is huge. The shadow cast by Saturn on its rings in this Cassini photograph stretches 83,000 miles, over 10 times longer than the diameter of the Earth.
Saturn is indeed a very huge planet. If Saturn were a hollow sphere, you could place 764 Earths inside it. And if you add the ring system, you truly have a very large system. In fact, Saturn plus its rings would just fit in between the Earth and the Moon.
And this gigantic planetary system demands long-term analysis. Cassini is scheduled to fly at least 76 orbits around Saturn, some for just a few weeks, other orbits farther from the planet up to several months. Cassini has already begun its groundbreaking scientific studies, returning breathtaking images, raising new questions about Saturn, its moons, and the planet's most obvious feature, its vast rings.
We think that Saturn's rings are very young compared to the age of the solar system. We think that perhaps a moon or a comet got in too close to Saturn, was torn apart by Saturn's gravity, and formed into a sheet of particles that orbits around Saturn. The rings are composed primarily of water ice, with a little bit of a coating, we think, that might be some kind of an organic material or maybe a silicate. And we think that the rings slowly are eroding over time, and if you go a few 100 million years into the future, perhaps Saturn's rings will look a lot more like Uranus's rings. Small, thin, narrow rings that are slowly eroding with time. The ring particles range in size from tiny dust grains to something the size of houses or even like huge icebergs circling about Saturn. The rings themselves are very thin relative to the planet. In fact, the rings in some places are only 100 meters thick, in others they may be as thin as 10 meters, which is very thin compared to Saturn.
If the mass of the rings were combined into one body, it would only be about 1/6 the size of our moon. And Cassini's detailed photographs of the rings begin to answer some of our questions about the configuration of the rings.
When you look at the rings themselves, you see many, many individual ringlets looking much like the grooves on a phonograph record. They look like many individual ringlets, but there's actually material in between most of those. The rings don't have names like other objects in our solar system, like the moon or a satellite like Mimas. Instead, they have letter names, and they were named in order of discovery. Cassini was the first to discover that there was actually a gap between Saturn's A ring and B ring, and that gap is named in his honor, the Cassini division, and also the Cassini mission is named in honor of Cassini.
Here is a Cassini photograph of the F ring through which the spacecraft passed. So thin it is invisible to virtually all telescopes, the F ring seems to dissipate and reappear in a strange, winding formation. Could this be a new ring forming, or perhaps an old ring dying? Cassini also photographed unexpected scalloped edges in the rings at what's known as the Encke gap. These wavy edges might be the gravitational effects of a small moonlet pulling at the ring as it moves along its edge. One of the biggest surprises so far is Saturn's outermost moon, Phoebe, photographed in a flyby before Cassini orbit insertion.
Well, Phoebe was really a very interesting world. It was really just a fuzzy dot in the Voyager images, the best pictures we had prior to Cassini's flyby. And as we got close, it turned out that Phoebe was a scarred and battered world covered with craters of all different sizes. And even craters on top of craters. And in some places, perhaps from the shake of an impact, pieces of the wall of a crater had fallen away, revealing what we think is water ice or carbon dioxide ice on Phoebe.
We were able to point the cameras precisely at Phoebe, so from a navigator's perspective, we couldn't have asked for a better flyby.
Scientists also believe this darkly colored moonlet, just 135 miles across, may be a captured object from the Kuiper Belt, made up of primordial chunks of matter still remaining from the birth of the solar system approximately 4.5 billion years ago.
So in a sense, with Phoebe, we have a time capsule where we have a chance to look at that material from which the solar system formed.
A planetary system so vast and so different demands a wide array of scientific equipment and a payload chassis large enough to carry it all. And how do you get such a huge spacecraft to travel over 2 billion miles? With a launch weight of 6 tons, Cassini could not use just traditional rocket fuel to propel itself to Saturn.
We'd have a spacecraft mass of tens of thousands of kilograms, almost all propellant. It would have been far too heavy for any launch vehicle to get off the surface of planet Earth.
So the Cassini team used some NASA know-how.
We did not take the short path. We took the long way around.
Coming up, we'll see how scientists used the power of the solar system to propel Cassini toward the ringed planet. Also, go inside the restricted facility where Cassini was built and find out how this advanced spacecraft was created and see the tools it will use to unravel the mysteries of Saturn. And later,
we can't see through the atmosphere to see the surface. It's shrouded in this mysterious orange smog.
we'll investigate the only moon in the solar system with its own atmosphere and find out what dangers and challenges Cassini and the Huygens probe face in this groundbreaking mission to the undisputed Lord of the Rings. (1997), Cape Canaveral, Florida. The largest interplanetary spacecraft ever launched by NASA is loaded into a Titan IV rocket, one of the most powerful launch vehicles ever constructed. Weighing 12,000 pounds, with an array of 18 different high-tech instruments, Cassini-Huygens dwarfed earlier missions in its ambition. But building this scientific ubercraft was only part of the $3.3 billion effort to reach the rings of Saturn.
5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn. We have cleared the tower, and the Cassini spacecraft is on its way to Saturn. T plus 20 seconds. All systems are go.
We did not take the short path. We took the long way around. We flew by Venus twice, then Earth, finally Jupiter and Saturn.
The distance between the Earth and Saturn is 900 million miles. So why did this craft fly nearly 3 times that distance to get to the ringed planet?
If Cassini was not able to use the 4 gravity assists it used during its nearly 7-year cruise, there's no way we could get the spacecraft launched. We'd have a spacecraft mass of tens of thousands of kilograms, almost all propellant. It would have been far too heavy for any launch vehicle to get off the surface of planet Earth.
And so Cassini used the dynamic power of the solar system to propel itself to the ringed world.
We fly by planets in ways to increase the energy and get us further it is out to the orbit of Saturn.
More than 5 months after the launch, the craft moved past Venus. The gravity of this second planet from the Sun gave Cassini what's known as a gravity assist, a kick that sped up and redirected its path.
It's very much of a slingshot effect. We come into the planet speeds us up and throws us out of the system.
And a firing of Cassini's main engine in what's called the deep space maneuver fine-tuned the craft's direction.
So using the gravity assist to make the big changes in the spacecraft, we're using the engines to make the very small changes.
These engines may look large, but they're actually much less powerful than they appear.
The Cassini main rocket engine is pretty wimpy by launch vehicle standards on planet Earth. It's about 100 pounds of thrust. If I strapped one on each leg, it wouldn't lift me off the ground.
And these important rockets helped bring Cassini on a trajectory back to Venus for another kick that carried the craft far away from the Sun to a familiar face.
We flew about 1,200 kilometers outside the Earth's surface, and we picked up about 7 kilometers per second, an additional velocity.
The 2 assists from Venus and 1 from Earth required a circuitous route for Cassini, but saved 18,000 pounds of fuel and provided the necessary velocity for an important flyby along the way.
The scientists were able to turn on the cameras, all of the instruments, and gain an enormous amount of scientific information from Jupiter.
During the late 1990s, the spacecraft Galileo arrived in orbit around this huge planet to analyze and map the strange and magnificent world. In what became known as the Millennium Flyby, Cassini added its scientific know-how to the effort. In tandem, the 2 advanced spacecraft three-dimensionally mapped the planet and its magnetosphere to return a flood of unparalleled data and images.
The work we did at Jupiter during the flyby was in fact a dress rehearsal of things we'd be doing later at Saturn.
And the maneuvers used by Cassini to acquire the extensive Jovian data didn't just happen in the blink of an eye. In fact, every one of Cassini's complex maneuvers must first start here, in a nondescript room hidden away deep inside the Jet Propulsion Laboratory in Pasadena, California.
We have what we call the spacecraft in the basement that simulates all of the commands that we send to it, because the worst thing we could do is send the wrong command to the spacecraft.
So, before Cassini ever makes a move, Leticia Montanez makes it first, on a fully operational Cassini hardware twin laid out in this clean room.
Think about the simulation as almost predicting the future. When we run it here, we are able to predict the events of what's going to happen to the spacecraft. Right here we have the Stellar Reference Unit. These navigate the spacecraft. This is the part that takes the pictures of the stars and determines where are we in space. We got some engine gimbal actuators here, and these are on the main engine.
These gimbals allow the engines to pivot in any 360-degree direction to allow the craft to make course corrections.
This right here is the power pyro subsystem. Basically, it controls the power on the spacecraft, and it also fires pyros for firing a cover off an instrument. Of course, we don't have the pyro part in this facility. It would be very dangerous to have that in here.
And all this hardware must go through real-time maneuvers with every test, including the one that brought Cassini just 1,240 miles from the moon Phoebe.
We ran this test about 3 different times, so that's 36 hours for each test run. Anything could happen. It would ruin 36 hours of testing. Long tests are very stressful.
The high-intensity preliminary maneuver testing performed by the spacecraft in the basement allowed Cassini to complete its side mission to Jupiter and then continue on its trajectory to its final destination.
Jupiter then gave us another 2 kilometers per second to finally get us to Saturn.
While in orbit, Cassini will return hundreds of thousands of images. But how can we receive such crystal clear photographs from nearly 1 billion miles away? How can this craft, floating in the vastness of space, transmit data and receive instructions from a distant Earth?
The signals that we're receiving from Cassini is considerably less than what you have to illuminate the dial of your wristwatch.
Coming up, inside one of the most powerful antennas ever constructed, and find out how signals from the Cassini spacecraft can be located and deciphered from so far away. Also, find out what Cassini will explore and may discover in its 4-year journey through the Saturnian system. And later, the future of space exploration is right now. We'll reveal possible upcoming missions that just may change the way we explore outer space forever.
The beginning of this orbital tour marks a very important point in human history. For the first time, we have an orbiting spacecraft around this miniature solar system of our planetary 9 neighbors.
To stop and have an extended stay like Galileo did at Jupiter, we haven't done. So a lot of the interest, a lot of what piques our curiosity is what we don't know, what we're going to find that never even occurred to us to think about before.
And so Cassini prepares to teach us much about the Saturnian system. But there are some things we already know about Saturn itself. This huge gaseous ball of hydrogen with a liquid iron and rock core possesses no definite separation between the land, ocean, and atmosphere. Saturn has only layers of hydrogen that transform gradually from a liquid state deep inside the core to a gaseous state farther out into its atmosphere. And its atmosphere is defined by massive bands of fast-moving weather systems produced by temperature-driven convective flows. It takes nearly 40 of our Earth years for Saturn to make one trip around the Sun. But a Saturnian day is just under 11 Earth hours. This high rotation rate creates strong centrifugal force that causes the giant to bulge near its equator and flatten at its poles. The planet's layer of liquid metallic hydrogen around its core may be responsible for producing much of Saturn's strong magnetic field, or magnetosphere.
Magnetospheres are basically bubbles of gas that are contained by a magnetic field of the planet or the object that has the magnetosphere. So in the case of Saturn, we have an internal magnetic field that's generating an invisible force field.
The gases are supercharged particles that whip through the magnetosphere, bumping into each other, causing huge energy emissions called aurora, on Earth known as the northern and southern lights.
Saturn's aurora are right in between Jupiter's and Earth's, in the sense that Earth's aurora are driven by the sun's interaction with our planet, and Jupiter's aurora are more driven internally by its own magnetosphere. Saturn seems to be a mixture of these two. So to really understand the process, we need to study Saturn.
And on Saturn, the massive energy storms that seem to ignite at its poles reveal the incredible dynamism of this gigantic world. The high-tech cameras and equipment that will tell us even more about Saturn and its system would be useless without the ability to transmit and receive the data streams, data that begins and ends here at JPL.
All of the data for tracking spacecraft, both for navigation purposes and telemetry data for science and engineering purposes, comes down through the Deep Space Network stations, comes in through this room, and then gets routed out to the different projects, the different users that are going to be the recipients of the data.
Cassini phones home and is phoned from home through the Deep Space Network's antenna farms.
They still on a 3 Hertz bandwidth?
That's affirmative.
Copy.
And one of the stations of the Deep Space Network is here, at Goldstone, in the heart of California's Mojave Desert, where engineers and operators constantly monitor Cassini with one of the largest radio antennas on Earth.
The dish is 230 feet across, at 70 meters, or if you wanted to make a better equivalent, it's about an acre of property. It's 50 feet from the base of the dish to the top of the cone. It's 5 stories. The dish weighs approximately 6 million pounds, and the rotating structure of that, it weighs about 8 million pounds, and that rotates on a film of oil about 5/1000th of an inch thick, and it just floats on that oil as we drive it with a gearing system.
The advanced computer software that instructs Cassini what to do in orbit was actually written during its 7-year cruise and transmitted to the spacecraft from here. Cassini reports back to the same antenna in tiny whispers from deep space.
The signal that we're receiving from Cassini is 1/billionth of 100 millionth of a watt in strength. That's considerably less than what you have on your wristwatch for illumination. Well, the signals consist of an RF signal, essentially, radio frequency signal. It's captured by the antenna, it's processed by the equipment. It is essentially turned into the same type of signal that you have for your home computer. It's 1s and 0s. It's a binary signal, and that signal then is sent through our equipment down to the scientist in JPL for analysis and processing.
Go ahead, Nav1.
We can confirm that we're receiving one-way data from the DSN.
Power that's transmitted out of the antenna is anywhere from 20,000 watts up to 400,000 watts in strength. Because it's so powerful, we have a number of safety interlocks in place that would prevent it from radiating in the event that a person was in the wrong place at the wrong time. If that were to occur, then someone could potentially be seriously injured.
And even though it may not look like it, this powerful antenna is in action.
Even though it's imperceptible, the antenna is actually rotating as it tracks the Cassini spacecraft, and it rotates at the same speed as the Earth.
The Goldstone antenna can only track Cassini so far. Then the Earth's rotation moves it out of range. That's where the rest of the network comes in.
As Goldstone loses view of the Cassini spacecraft, it's picked up by one of the subsequent tracking stations. The Deep Space Network consists of 3 tracking stations, one here in Goldstone, there's one in Madrid, Spain, and there's one in Canberra, Australia.
And with all these stations and all these different vehicles in deep space, how do scientists know they're talking to just Cassini?
There's a number of signals that are actually received by our antenna, but like a radio, you can tune into the appropriate frequency to capture the actual Cassini frequency.
Every spacecraft tracked by the Deep Space Network is designated with a randomly assigned identifying number. Cassini's designation? 82. Without the Deep Space Network, Cassini could not remain operational and return the amazing data back to Earth. We've seen how it launched, how it got there, and how we tell it to do what it does. But how was Cassini built and tested? What dynamic process powers the equipment on this spacecraft? And what incredible equipment does it have? How will it use that hardware to investigate Saturn, its rings, and its many varied and exotic moons? Coming up, we'll enter the inner sanctum where Cassini was constructed and find out how the Cassini spacecraft and the Huygens probe have revolutionized deep space travel for the next generation of robotic explorer. And later,
there is no second chance with this. The Huygens probe is a one-shot deal. We have to make sure we hit the entry corridor, and there's no way out of that.
Slam into the Titan atmosphere at more than 11,000 miles per hour as the Huygens probe is finally unleashed.
Well,
Okay, we have burn complete here for the SOI orbit insertion burn. Congratulations, continue in mission control. The high fives begin in the back of our mission support area.
After a 7-year journey, Cassini's Saturn orbit insertion on June 30th, 2004 marked a new era in deep space exploration.
This is the most ambitious, the most aggressive mission that NASA has ever launched out into interplanetary space.
Science is all about discovering the unknown, and it's difficult to build an instrument and a spacecraft and a probe that will survive the unknown long enough to actually make the measurements.
But already Cassini has made astounding measurements, and it's got the most advanced equipment to do it. In this clean room at JPL in 1995, engineers assembled the Cassini spacecraft, now in orbit around Saturn. But at the California Science Center, visitors can see firsthand the full-scale model of this groundbreaking spacecraft and all its hardware.
When you get up here beside the Cassini spacecraft, get this close to it, you get a better perspective of just how large it really is. There are a total of 18 instruments on it. 12 of these are on the orbiter. 6 of them are in the probe that will measure, assess, analyze the atmosphere of Titan. This large dish sitting up on top of the spacecraft is the high-gain antenna. This is used primarily to serve as the communications link, both from Cassini to the ground, as well as for sending instructions from the ground up to Cassini. This also serves double duty. At times when we're going through portions of the plane of the rings that is potentially hazardous due to the presence of dust, debris material, we will point this antenna in the direction in which the particles will be coming from to shield the rest of the spacecraft behind it. This dish is just over 13 feet in diameter. It's made of a graphite epoxy, so it's a very solid, rigid structure and is well capable of protecting us against the kind of small, grain-sized dust particles we expect to find in the Saturn environment.
That is the sound of space. Actual dust particles hitting Cassini's high-gain antenna as the craft came into orbit around Saturn. And that's exactly the sort of dust that Cassini looks for with this.
The round cylindrical instrument is the CDA, Cosmic Dust Analyzer. This instrument analyzes cosmic dust particles for composition, velocity, energy, and direction of travel.
There is a great deal of dust in Saturn's system, dangerous dust. But Cassini wears the ultimate flak jacket.
The covering is mylar. That serves 2 purposes. One is for thermal control of the device, and the other is to protect it from impacts of small particles of dust and grains during flight.
The layers ensure that any particles penetrating this outer skin would be reduced to harmless dust by the time they reached the craft's delicate, sensitive scientific equipment. Equipment like this boom magnetometer, which measures magnetic energy and will detect the magnetosphere of the planet and its moons.
This is a boom that extends 36 feet from the spacecraft, and it supports 2 different magnetometer detectors. The purpose of putting them out on this boom is to get them out a ways from the spacecraft so that we're not detecting magnetic signals generated by the spacecraft, but rather are just picking up whatever data is there from the natural environment.
The mylar covering also protects Cassini's suite of 4 optical sensing units, or cameras, that have already returned thousands of riveting photographs. These sensitive cameras must be maintained at constant and exact temperatures, or they would simply stop working.
The silver-colored louvers are for thermal control. These open and close automatically on board the spacecraft to keep the internal temperature at specified levels.
And it's not just the mylar sweater and these louvers that keep Cassini comfortable. So far from the warmth and light of the sun, just 1% of what we feel here on Earth. This lonesome traveler needs a reliable and consistent energy supply for heat and power.
The black cylindrical device is one of 3 RTGs, which stands for Radioactive Thermoelectric Generator. These devices use plutonium to generate electrical power for the spacecraft. At launch, each of these devices put out about 285 watts of electrical energy. Over time, as the radioactive material decays, which is the process that generates the heat, which is then converted to electricity, the net result is that they put out a decreasing amount of power over time.
The RTGs produce less wattage than most kitchen microwave ovens. But it is by far enough power to supply Cassini with electricity for its science-gathering mission to explore Saturn and its abundant moons.
When Cassini was first launched, we knew of 18 moons. During its 7-year cruise phase, we've discovered 13 more from the Earth.
Cassini has already photographed and analyzed the ice rock Phoebe. However, Phoebe is but one grain of sand in the vast ocean of Saturn's orbiting satellites. The craft will make close flybys of some of the more enigmatic moons.
These additional moons are all well distant from Saturn, what we call a group of irregular moons that are in orbits, some of them backwards or retrograde, some of them inclined relative to Saturn.
Enceladus, where giant ice volcanoes or perhaps geysers periodically reshape the landscape and even blast material far into space to be captured by Saturn's rings. Rhea, an asteroid-pocked world with wispy white streaks that may be a result of snow coming from cracks in its frozen crust. And Dione, another heavily cratered moon showing similar feather-like landscapes. Tethys, where an icy canyon called Ithaca Chasma, 60 miles wide and perhaps 3 miles deep, cracks this moon from pole to pole. Mimas, with a crater so large its creation almost shattered the moon into bits. Cassini may also fly by Hyperion, with ice cliffs that reach into space nearly 6 miles high. And already Cassini has photographed this curious moonlet, Iapetus. That is not a shadow caused by the light of the sun. This Saturnian satellite possesses one hemisphere as black as coal and another as white as new-fallen snow.
I think in close to the planet, Cassini will discover many more moons, especially in a region between the A ring and the F ring. We think that might be actually a belt of moonlets, and there may be tens or even 100 moons for Cassini to discover.
But one moon above all others has riveted scientists worldwide. And the International Huygens probe, now attached to the Cassini orbiter, will soon descend into its murky, shrouded depths.
It's like the primordial, prebiotic Earth atmosphere in a deep freeze.
Titan, an elusive moon that just might hold the secrets of our own evolution. With Cassini safely in orbit around Saturn, the spacecraft team now turns to science observations. An international team of more than 250 scientists from the United States, 20 European countries, and Israel has ambitious plans for the large, sophisticated spacecraft. A centerpiece for the mission, the moon Titan.
Titan is the second largest moon in the entire solar system. The only larger moon is Jupiter's moon Ganymede. Titan is larger than the planets Mercury or Pluto. And so if it was orbiting the Sun, most people would consider it a planet itself. An interesting feature of Titan is its thick atmosphere. In fact, it's the only moon in the entire solar system that has an atmosphere, and it's mostly nitrogen, much like the Earth. Sometimes Titan's atmosphere is considered prebiotic. In other words, it's very rich in organic material. Not necessarily biological molecules, but hydrocarbons, which is the basis of the organic materials that we know here on Earth. It has methane, ethane, acetylene. All of these are considered hydrocarbons and organic compounds. The whole landscape with a little oxygen is completely flammable. It's like a giant barbecue waiting to happen. And to study it is like looking at our origins. It's a little bit like Earth in a frozen embryo state.
To study Titan, the European Space Agency developed the Huygens probe. Late in 2004, pyrotechnic charges will blow the bolts, and Huygens will become the first probe ever to descend to the moon of another planet.
One of our most daunting challenges remaining for the Cassini mission is the release of the Huygens probe. Imperative we point the orbiter in the proper direction to release Huygens so that it may ballistically free fall towards the moon Titan. We look forward to its touchdown or possible splashdown on January 14th of 2005.
Sean Stanley details Titan's hot and wild ride.
The probe will slam into the atmosphere 18,000 kilometers per hour. The heat shield will take the brunt of the entry energy, and the outermost layers of the thermal blankets will burn off. The probe will decelerate to about 1,500 kilometers per hour, and the outermost heat shield will reach temperatures of 1900 Celsius.
Now reaching temperatures of 3,400 degrees Fahrenheit, the reduction of speed from 11,000 miles per hour to just under 1,000 miles per hour will prompt the probe to release a pilot chute.
The pilot chute will pull off the back cover and the main chute will be deployed. This has a diameter of about 8 meters and it will decelerate the probe to 300 kilometers per hour. Then the heat shield will drop away, the covers will deploy, and the probe will start making science measurements. This phase lasts for about 15 minutes, and then the main chute's cut away and a smaller drogue chute is deployed. Science measurements will continue through this part of the atmosphere. There may be lightning and electrical activity. The probe may hear thunder. It'll take direct sampling of the atmosphere. As we approach the surface, a lamp will turn on the descent imager, and we'll be able to take images of the surface in the last few meters, and then we'll impact at 5 to 6 meters per second. And the surface science package will start taking surface measurements. This shows us landing on a solid, but if we land on a liquid, we'll be able to measure the refractive index and other liquid properties. The surface phase could last between 3 and 15 minutes is what is designed, but if we survive the landing and land at the correct angle, we have enough battery power to transmit for up to 2 hours.
The greatest part of Huygens science gathering will be done on the descent, a period of 2.5 hours. The remaining science is dependent on the probe surviving its impact with Titan's surface. What kind of bump is it likely to experience?
Imagine leaving the parking brake off on your car and rolling into a wall after a few feet. You'd feel a pretty good jolt. But whether we land on rock or on some kind of soft hydrocarbon surface or on a liquid surface on Titan, there's a very good chance that the probe will survive.
Huygens is a fraction of Cassini's weight, only 705 pounds to the orbiter's 6 tons at launch. But it packs an impressive array of instruments in a meticulously engineered package.
This is a 1/4 scale model of the Huygens probe. The real thing is about 3 meters across, but you can get a pretty good idea of what the probe's about from this model. The saucer shape of the probe that we chose, it's the shape that gave us the best aerodynamic performance for entering the atmosphere of Titan. During the entry, the gold-colored foil will burn away and it will expose these expanded silica tiles. And it's this heat shield material that will take the brunt of the heating during the re-entry. You can see a pilot chute mortar in here. The pilot chute at the right time is fired out of the canister and it blasts out this trefoil section here. These three pieces break away. The pilot chute bag comes flying out and it pulls after it the lines and risers. You can see them taped down to the back surface of the probe. These all spool out, the parachute deploys, and then the back cover is pulled off and pulled away from the probe. Just on the side of the probe here, you can see the descent imager and spectral radiometer head. This is the camera head. Essentially, it has a 45-degree down towards the surface set of images, out towards the horizon, and takes spectra 45 degrees up.
Huygens will report its findings back to Earth using Cassini as a relay station. Cassini's 4-year mission will investigate new moons and fly high above the rings to study phenomena such as these spoke-like brush strokes, radial rotating features that may be caused by a combination of magnetic and electrostatic forces. Cassini will use gravity assists from Titan to gain velocity to change its orbit, moving farther out from Saturn to investigate the moons, and then returning closer to the planet to examine Saturn itself.
Without the great moon of Titan, we could never do the things we were attempting to do on this mission. Titan allows us to change the sizes of the orbits, rotate it so that we're looking down onto the rings on the top of Saturn, rotate the orbit so we're looking from the backside, get all of the different views of the whole Saturnian system and investigate all the various phenomena the scientists would like.
And Cassini also retained some of its original propellant to make necessary course corrections along the way.
Cassini launched with 1,869 kilograms of nitrogen tetroxide, or oxidizer, and 1,131 kilograms of monomethyl hydrazine, our fuel, for a total bipropellant load of 3,000 kilograms, or 6,600 pounds. We used about 1/3 of that total in the mere hour-and-a-half firing for orbit insertion. We used about 1/3 of the propellant in the 6.7 years before that time, leaving us about 1/3 of the bipropellant left for the 4-year orbital tour and possible extended mission.
And if the spacecraft remains healthy, the extended mission might include higher-risk maneuvers. Cassini might fly closer to Titan and study the composition of its choking atmosphere. Or perhaps soar even closer to the rings, or even through the rings at the ring gap called the Cassini Division, named, like the spacecraft itself, for the 17th century astronomer.
Really getting a close look at the rings and perhaps discovering new moons and new rings about Saturn, all part of the process of discovery.
Or, in one last feat of spectacular science, Cassini will end its journey, hurtling through the Saturnian atmosphere to the shrouded planet itself. Cassini-Huygens, an international mission of discovery, has proven to be a groundbreaking achievement that sets the stage for a variety of even more ambitious excursions to the outer planets. One project currently under consideration utilizes an orbiting spacecraft that sends one or more advanced probes into the atmosphere of Titan. Referred to as aerial mobile technology, or Aerobot, rugged balloons carrying labs could fly below Titan's smog-like clouds and study the strange features of the landscape. Unlike Huygens, with a surface life of just 2 hours, these high-tech dirigibles could carry instrumentation on extended tours lasting weeks or months and cover thousands of miles. And Cassini-Huygens is just the beginning.
The Saturn orbit insertion burn begins a 4-year orbital tour of the solar system's most intriguing target, a miniature solar system awaiting exploration. It has much to tell us about the origin and history of our solar system, and perhaps even the origin of life on Earth. Stay tuned.